Woohoo, I'm live! And today we're going to talk all about bear math. Very specifically, we're going to be simplifying radicals, or as some people call them, square roots or cube roots, with bears. So, here's my bear, here's my spider. And for bear math, you can kind of see underneath the paper, pretend you can't. This is the magic of television, everyone. Okay, get this straightened out. So here's the initial question. If a bear is chasing you and a friend through the forest, this is a little joke. You don't have to be faster than the bear. You just have to be faster than your friend. Ha 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 ha. Let me show you. Ha ha ha. They think it's hilarious. Spider and bear both think it's hilarious. Oh, such a funny joke. Rawr. Oops, sorry, wrong way. Rawr. Okay. So, what the heck does this mean for actual math? It's a good question. So let's start out with an example. And the example is, my example is going to be to simplify. Now, simplifying radicals is tricksy. If we get something like radical 9, in other words, the square root of 9, we know that that equals 3. It's nice and clean. We don't have anything left over. Life is just great. However, if we have something like radical or square root of 40, this gives us a bigger problem because 40 is not the perfect square of a whole number. It is the perfect square of a number. It's a number between 6 and 7, closer to 6, I think. The calculator knows what it is, but it's very hard for human people to really grok that. And a lot of times what we would like is not just an estimate, we would like the exact value, especially in math. So here's a technique for simplifying a radical when you don't know the exact square root or principal square root. So this is what you're going to do. First thing is I'm going to have to point some things out. For example, this thing, which we call a radical, is now a cabin. It's a cabin in the woods. And a terrible thing has happened. And in this cabin, you're all there with all your friends, you're having a great time, and suddenly the Wi-Fi is down. Oh no. Oh no. Okay, so the Wi-Fi is down. Oh no, oh no. So what are we going to do? Well, we're going to have to get everyone out of the cabin. The bad news is there's a bear in the forest. Hello. Okay, so there's the bear in the forest. Arr. And so the thing is, if you just run through the forest or walk through the forest, let's see. Push this down further. La 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 la. Then, as you're walking through the forest, la la la, the bear will come, and it will eat you. Now, this is a problem because then you're eaten and you don't get to go, have more ice cream. So if our goal is to get more ice cream, our goal is to get out of the cabin through the forest safely. Now, here's the thing. The bear is not very smart. Don't tell him, but he's not very smart. And here's the thing. If you and an identical friend run through the forest, the bear will not be able to choose between you. And so it will choose the slower one. It will just catch whichever one is viewed as slower. So the key is run with an identical friend. So to escape, run with a twin. Okay, so what the heck does that mean for our problem over here? Well, for our problem over here, we've got radical 40, And the first thing is I got to figure out what actually is going on. Who's in the cabin? So first thing is I'm going to break this down. 40 is equal to 4 times 10. 4 is 2 times 2. Scooch this up a little bit. 10 is 2 times 5. So I used a factor tree to figure out who's actually in the radical. So inside that square root or that radical, I've got a 2 and a 2 and a 2 and a 5. Okay, so the bear is waiting outside yum, 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 to eat anyone who runs. But the thing is the bear can only catch one of you if two of you run. Now, if you just run individually, the bear will eat you. If you and a friend who don't look the same run, then the bear will just have to choose one of you, and that might not go very well. So we're only going to let twins run. So here's the thing. This 2 and this 2, they are twins. So we're going to let them run. Now, I could have picked any two of these. So any two of those would work. These two are going to run. Ah, run, 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 run. Here comes the bear. Yum, 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 yum. Okay, so sad but true. One of those twos did not make it. One of them gets out. Now, what about the 2 and the 5? Well, the 2 and the 5, although they kind of look alike, especially if you have dyslexia or dyscalculia, they can look very similar, but they're not identical twins. And so it's not advisable that they run. So we're going to leave them in the cabin. And we're going to call back. We're going to say, don't worry, we'll send help. Now, here's the thing. Don't tell them we're not actually going to send for help. They're numbers, though. It's okay. They're going to be fine. So the end result of this is that I end up with a simplified radical two times radical 10 or 2 times the square root of 10. And that's how you simplify a radical. Woohoo. So let's try another one that's a little more complicated. The next one I want to work with is radical or square root of 1200. There's a lot of people at this cabin. This was a big party cabin. Here's the thing about figuring out who's inside. First thing, double check that this is not a perfect square. It is not, but you can double check. Dora style. So, boys and girls, is this a perfect square? No. Okay, so I'm going to go ahead and start breaking this down. When numbers end in zeros, it's very straightforward to break them down because you just break out that 100 right there. So I'm going to break out 12 times 100. The 100 breaks down as 10 times 10. The 12 breaks down as 3 times 4. And then I stop for a moment and I say, if I've already found twins, you can stop. So you can stop with the 10s or you can keep going. Each of the 10s has a 2 and a 5. So you can stop when you get to twins or go all the way to a complete factorization. This technique works either way. So here is my cabin, my radical, and I'm going to write all of these numbers. So I've got a 3 and a 2 and a 2 and a 2 and a 5 and a 2 and a 5. Now, if you've got a whole string of prime factors like this, what you might want to do is write them in, again, descending order. Descending order works for everybody. Let's see, I got a 5 and a 3 and a 1, 2, 3, 4. Looks like 1, 2, 1, 2, 3, 4. 4 2s. Okay. So is that correct? 4 times 4 is 16, times 3 is 48. I'm missing somebody. Oh, I see what I'm missing. I know you guys over all on in TV land, you're all like, there's a 5. You forgot the 5. No, I didn't. I was just checking to make sure you knew there was another 5. There we go. Okay, thank goodness. That could have been disastrous. So as we look over everyone who's in the cabin, we see that I've got a couple of twin 5s. I'm going to let them go running. Ah! yum, 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 yum. So the 2 5s go running. Only 1 5 makes it out. Okay, who else is a twin? I see 2 twin 2s. They go running. Ah! Yum, 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 yum. Only one of them makes it out. And here's another 2 twins right there. Ah! Yum, 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 yum. And the bear eats one of them. And the only one who's left over is the one that doesn't have a twin. And again, we leave it in the cabin and we say, don't worry, we'll send help. Even though we know we're not going to send help because these are numbers. It'll be fine. The 3 can entertain itself. Trust me. If anyone could entertain themselves, a 3 could entertain themselves. Okay, so what's going on here? Well, now I've got a 5 times 2 times 2. Or, in other words, either I could do 5 times 2 is 10 times 2 is 20. Or I could do 2 times 2 is 4 times 5 is 20. So I got 20 on the outside. And then radical 3 or square root of 3. And that's 1200 inside a radical. The square root of 1200 simplifies to 20 radical 3. This is the exact value. And I hear you saying, okay, this is fine. But what about those of us who have to deal with other kinds of radicals? They're not all square roots. The world is full of other things. For example, this bad boy right here, the cube root of 54. So this is the cube root of 54. And we can simplify this as well. This number right here is known as the index. And this just means that this is a bigger bear. Now, in this first problem, or the second problem, I guess, on this page, the first problem on the page, that's my spider. This bear was a square bear. This is square bear. Rawr! Now, I don't have another one. I really should have another one. And perhaps I will make another prop for another day. But we're going to pretend that this bear, I'm going to need a cube bear. And the cube bear eats more. For a cube bear, 3 run, 1 makes it. So remember with the square root or with the radical, 2 numbers went running, and 1 makes it out. This one, we're going to need to run with 3. Whatever the index is, that's how many run. Okay, so first thing, 54. Let's break it up. That's 9 times 6. 9 is 3 times 3. 6 is 2 times 3. Okay, so what I've got is I've got the cube root of 3 times 3 times 3 times 2. Woohoo. So this is a cube root. And so 3 of these, 3 twins, or I guess they're triplets now, have to run. Yum, 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 yum. Only 1 makes it out. And again, because 2 doesn't have any friends in the cabin, we leave it in. We say, don't worry about it. And this is the cube root of 54 simplifies to 3 times the cube root of 2. You did it. Woohoo. You're awesome. Yay, bear math.